Bismillahirrahmanirrahim. In the name of Allah, the most gracious, the most merciful. Assalamu alaikum. Today we will cover quantum blackbody radiation. We'll start with derivation of Maxwell-Boltzmann distribution. Let's consider a canonical ensemble. A large reservoir at temperature T is connected to a small system. We now consider two systems coupled as before in such a way that they can exchange energy. This time we'll make one of them enormous and call it the reservoir, also known as heat bath. It is so large that you can take quite a lot of energy out of it, and yet it can remain at essentially the same temperature. The other system will be small. We will assume that for each allowed energy of the system, there is only one single microstate, and therefore system has the value of omega equal to 1. We fix the total energy of the system and reservoir to be E. The energy of reservoir can be taken as E minus epsilon. The energy of the system is taken as epsilon. The situation of a system in thermal contact with large reservoir is known as the canonical ensemble. The probability P epsilon that the system of energy epsilon is proportional to the number of microstates which are accessible to the reservoir multiplied by the number of microstates which are accessible to the system. Therefore, probability of epsilon is proportional to omega E minus epsilon. These are the number of microstates of the reservoir multiplied by 1, which is the microstate of the system. If we do Taylor expansion of ln omega E minus epsilon, it is equal to ln omega E minus derivative of ln omega E times epsilon with respect to E. The derivative of ln omega with respect to E is equal to 1 over kBt. If we substitute this value in the Taylor expansion, ln omega E minus epsilon is equal to ln omega E minus epsilon over kBt. If we take the exponential of the equation, we get omega E minus epsilon is equal to omega E multiplied by exponential minus epsilon over kBt. The probability that the system has energy epsilon is proportional to number of microstates of the reservoir, which is equal to omega E minus epsilon. By Taylor expansion, we find that the probability that the system has energy epsilon is proportional to omega E exponential E minus epsilon over kBt. Therefore, the probability that the system has energy epsilon is proportional to E minus epsilon over kBt. This is known as Boltzmann distribution. E minus epsilon over kBt is known as the Boltzmann factor. Since the system is now in equilibrium with the reservoir, it must also have the same temperature as the reservoir. Although the system has fixed temperature T, its energy epsilon is not constant. We now have a probability distribution which describes exactly how small system behaves when coupled to a large reservoir at temperature T. The system has a reasonable chance of achieving the energy epsilon, which is less than kBt, but the exponential in the Boltzmann distribution begin to quickly reduce the probability of achieving energy much greater than kBt. However, to quantify this properly, we need to normalize probability distribution. If a system is in contact with a reservoir and has microstate R with energy epsilon R, then probability of microstate R is equal to exponential minus epsilon R over kBt divided by sum over n exponential minus epsilon n over kBt, where the sum in the denominator makes sure that the sum is normalized. The sum in the denominator is called the partition function and is denoted by Z. An oscillator in the wall can receive energy from the radiation in the cavity absorption, or it can give away energy to the radiation in the cavity emission. The absorption process sends the oscillator to a higher quantum state. The emission process sends the oscillator to a lower quantum state. Change in energy is equal to h nu, where h is Planck's constant and nu is the frequency. When the frequency is less, the quantum states are really close to each other, making absorption very easy. However, when nu is large, the quantum states are further apart, making absorption less likely. December 14, 1900, Planck was able to prove revolutionary concept. The oscillators comprising the black body and re-emitting the energy incident upon them could not absorb this energy continuously but only in discrete amount. Planck's new idea was to assume the possible energies of the oscillators were quantized, that is, the oscillator of frequency nu could only have energy epsilon n is equal to nh nu, where n is 1, 2, 3 and so on. The average energy per oscillator was calculated from the Maxwell-Boltzmann distribution. Epsilon bar is equal to sum over n epsilon n exponential minus epsilon n over kBt divided by sum over n exponential minus epsilon n over kBt. The denominator is the partition function and is often represented by z. It is easily evaluated by summing the geometric series. If n naught, n1, n2 and so on are the number of oscillators per unit volume possessing energy 0, h nu, 2 h nu and so on, then the total number of oscillators n per unit volume is n is equal to n naught plus n1 plus n2 and so on. We can calculate the partition function using the geometric series. Z is equal to sum n is equal to 0 to infinity exponential minus epsilon n over kBt. Exponential to the power of 0 is 1. Therefore, the series is 1 plus exponential minus epsilon 1 over kBt plus exponential minus epsilon 2 over kBt and so on. We know epsilon 1 is equal to h nu, epsilon 2 is equal to 2h nu. Therefore, the series is 1 plus exponential minus h nu over kBt plus exponential minus 2h nu over kBt plus exponential minus 3h nu over kBt and so on. If we set exponential minus h nu over kBt to be y, the geometric series become 1 plus y square plus y cube and so on. We know that the sum of yn from n is equal to 0 to infinity is equal to 1 over 1 minus y is equal to exponential minus h nu over kBt. Therefore, the partition function becomes 1 divided by 1 minus exponential minus h nu over kBt. These are the total number of oscillators. Let's find the numerator. Numerator is equal to sum of epsilon n multiplied by exponential minus epsilon n over kBt from n is equal to 0 to infinity. Epsilon n is equal to nh nu. Therefore, the numerator becomes sum of nh nu multiplied by exponential minus nh nu over kBt from n is equal to 0 to infinity. This is equal to h nu multiplied by exponential minus h nu over kBt plus 2h nu multiplied by exponential minus 2h nu over kBt plus 3h nu multiplied by exponential minus 3h nu over kBt and so on until nh nu multiplied by exponential minus nh nu over kBt. If we substitute exponential minus h nu over kBt as y, then the numerator is equal to h nu multiplied by bracket y plus 2y square plus 3y cube and so on. This is equal to h nu sum nyn from n is equal to 0 to infinity. We know sum of yn from n is equal to 0 to infinity is equal to 1 over 1 minus y. If we take the derivative, we find that the sum of n minus 1 from 0 to infinity is equal to the sum of derivative of yn with respect to y from 0 to infinity. If we exchange summation and derivative sign, we get d over dy sum of yn from n is equal to 0 to infinity. Sum of yn from n is equal to 0 to infinity is 1 over 1 minus y. Therefore, derivative of 1 over 1 minus y with respect to y is equal to 1 over bracket 1 minus y bracket close square. In the last slide, we show summation n minus 1 from n is equal to 0 to infinity is equal to 1 over bracket 1 minus y bracket close square. If we multiply both sides by y, we get summation n from n is equal to 0 to infinity is equal to y over bracket 1 minus y bracket close square. When n is equal to 0, summation n is also equal to 0. Sum n from 1 to infinity is equal to y over bracket 1 minus y bracket close square. Y is equal to exponential minus h nu over kbt. Therefore, sum n from 1 to infinity is equal to exponential minus h nu over kbt divided by bracket 1 minus exponential minus h nu over kbt bracket close square. H nu multiplied by sum n from 1 to infinity is equal to h nu multiplied by exponential minus h nu over kbt divided by bracket 1 minus exponential minus h nu over kbt bracket close square. Epsilon bar, the average energy, is equal to sum of epsilon n multiplied by exponential minus epsilon n over kbt over all values of n divided by sum of exponential minus epsilon n over kbt over all values of n. We know epsilon n is equal to nh nu. Therefore, the mean energy is equal to sum of nh nu multiplied by exponential minus nh nu over kbt over all values of n divided by sum of exponential minus nh nu over kbt over all values of n. We calculated the numerator and the denominator in the previous slides. E bar is equal to numerator, that is h nu multiplied by exponential minus h nu over kbt divided by bracket 1 minus exponential minus h nu over kbt bracket close square divided by the denominator, that is 1 over 1 minus exponential minus h nu over kbt. 1 minus exponential minus h nu over kbt cancels, and we are left with E bar is equal to h nu multiplied by exponential minus h nu over kbt divided by 1 minus exponential minus h nu over kbt. If we multiply the numerator and the denominator with exponential h nu over kbt, we get E bar is equal to h nu divided by exponential h nu over kbt minus 1. The number of modes calculated by the classical theory was correct. However, the mean energy calculated by the classical theory was incorrect because energy is quantized. Energy per unit volume per unit frequency is equal to u nu d nu is equal to 8 pi nu square E bar divided by C cube d nu. E bar is equal to h nu divided by exponential h nu over kbt minus 1 bracket closed. H is Planck constant, nu is the frequency, kb is the Boltzmann factor, T is the temperature, C is the speed of light, and pi is 3.14. Energy per unit volume is, if we substitute the value of E bar into u nu d nu, we get u nu d nu is equal to 8 pi nu square h nu divided by C cube bracket exponential h nu over kbt minus 1 bracket close d nu. U nu d nu is equal to 8 pi h nu cube divided by C cube bracket exponential h nu over kbt minus 1 bracket close d nu. Total energy per unit volume energy density is the integral over all the frequencies. U is equal to 8 pi h over C cube integral nu cube divided by bracket exponential h nu over kbt minus 1 bracket close d nu. If we take h nu over kbt as x, then nu is equal to x kbt over h and d nu is equal to kbt over h dx. Nu cube is equal to bracket x kBt over h bracket close cube exponential h nu over kBt minus 1 is equal to exponential x minus 1 d nu is equal to kBt over h dx. If we substitute all these values into u, we get u is equal to 8 pi h over c cube integral bracket x kBt over h bracket close cube multiplied by kBt divided by h bracket ex minus 1 bracket closed dx. U is equal to 8 pi h over c cube integral bracket kBt bracket close to the power of 4 divided by h to the power of 4 multiplied by x cube divided by exponential x minus 1 dx. Since bracket kBt to the power of 4 divided by h to the power of 4 does not depend upon x, we can take it out of the integral. U is equal to 8 pi kb to the power of 4 t to the power of 4 divided by c cube h cube integral x cube divided by exponential x minus 1 dx. Integral x cube divided by exponential x minus 1 dx is just a number and is equal to pi to the power of 4 divided by 15. Energy density U is proportional to temperature to the power of 4 and is related by the constant A, that is equal to 8 multiplied by pi to the power of 5 multiplied by kb to the power of 4 divided by 15 c cube h cube. A has a value of 7.566 into 10 raised to the power minus 16 joule meter minus 3 Kelvin minus 4. Energy density is energy per volume and is denoted by U. Energy flux is equal to energy divided by area time and is denoted by E. E, the energy flux, is equal to C, that is the speed of light, multiplied by energy density, that is U, divided by 4. A is equal to Cu over 4 is equal to C over 4 multiplied by bracket 8 multiplied by pi to the power of 5 multiplied by kb to the power of 4 divided by 15 c cube h cube bracket close multiplied by t to the power of 4. This is equal to 2 multiplied by pi to the power of 5 multiplied by kb to the power of 4 multiplied by t to the power of 4 divided by 15 c square h cube. Energy flux E is proportional to temperature T to the power of 4 and is related by the constant sigma. Sigma is equal to 2 multiplied by pi to the power of 5 multiplied by kb to the power of 4 divided by 15 c square h cube and has a value of 5.67 into 10 raised to the power minus 8 watt per meter square Kelvin square. Sigma is Stefan-Boltzmann constant and the theoretical value agrees with the experimental value. U nu is equal to 8 pi h nu cube divided by c cube bracket exponential h nu over kBt minus 1. At low frequency, we can do Taylor expansion of exponential h nu over kBt and we get 1 plus h nu over kBt plus higher order terms. Therefore, exponential h nu over kBt minus 1 is equal to 1 plus h nu over kBt minus 1. 1 cancels and we are left with h nu over kBt. Since exponential h nu over kBt minus 1 at low frequency is equal to h nu over kBt, we get U nu is equal to 8 pi h nu cube divided by c cube divided by h nu over kBt. 1 nu cancels and we are left with 8 pi nu square kBt divided by c cube. This is Rayleigh-Jean's law at low frequency. U nu is equal to 8 pi h nu cube divided by c cube bracket exponential h nu over kBt minus 1 bracket close. At high frequency, we can forget about the factor of minus 1 in the expression exponential h nu over kBt minus 1. Therefore, we get U nu is equal to 8 pi h nu cube divided by c cube exponential h nu over kBt. This is equal to 8 pi h nu cube exponential minus h nu over kBt divided by c cube. As nu approaches infinity, exponential minus infinity approaches 0. Planck's blackbody spectrum agrees with the experimental spectrum. Intensity is proportional to T to the power 4, where T is the temperature. At low frequency, the graph behaves like Rayleigh-Jean's law, and at high frequency, the intensity approaches zero. As the temperature increases, the maximum intensity occurs at a higher frequency. In the intensity wavelength graph, as the temperature increases, maximum intensity is achieved at a lower wavelength since frequency and wavelength are inversely proportional. U nu is equal to 8 by h nu cube divided by c cube bracket exponential h nu over kBt minus 1 bracket close. Flux E is equal to Cu over 4. E is equal to 2 pi h nu cube divided by c square bracket exponential h nu over kBt minus 1 bracket close. When flux is maximum, the derivative of flux with respect to frequency is equal to 0 at the peak. This is equal to 2 pi h over c square derivative of nu cube divided by exponential h nu over kBt minus 1 with respect to frequency. Since we have frequency in the numerator as well as in the denominator, we will do derivation by parts. Since the derivative is equal to 0, we get h nu multiplied by exponential h nu over kBt divided by kBt bracket exponential h nu over kBt minus 1 bracket close is equal to 3. If we cross multiply, we get h nu over kBt is equal to 3 multiplied by bracket exponential h nu over kBt minus 1 bracket close divided by exponential h nu over kBt. If we multiply the numerator and the denominator with exponential minus h nu over kBt, we get h nu over kBt is equal to 3 multiplied by bracket 1 minus exponential minus h nu over kBt bracket close. If we substitute h nu over kBt as x, we get x is equal to 3 multiplied by bracket 1 minus exponential minus x bracket close. This gives the value of x to be equal to 2.821. Therefore, h nu over kBt is equal to 2.821. If we cross multiply, we get nu max is equal to 2.821 multiplied by kBt divided by h, which means nu max is proportional to temperature T. Nu max is the frequency at which the intensity is maximum. As the temperature increases, nu max also increases. That means maximum intensity occurs at a higher frequency as the temperature increases. If we try to get the same expression in terms of lambda, that is the wavelength, instead of frequency, that is nu, E is equal to 2 pi h nu cube divided by c square bracket exponential h nu over kBt minus 1. C is equal to nu lambda, c is the speed of light, nu is the frequency, lambda is the wavelength. D nu is equal to minus c over lambda square d lambda. Nu is equal to c over lambda. E d nu is equal to 2 pi h bracket c over lambda bracket close cube divided by c square bracket exponential hc over lambda kBt minus 1 bracket close d nu. If we multiply and cancel few terms, we get E d nu is equal to 2 pi h c square divided by lambda 5 bracket 1 minus exponential hc over lambda kBt bracket close d lambda. E nu d nu is equal to minus E lambda d lambda. Therefore, E lambda is equal to 2 pi h c square divided by lambda 5 bracket exponential hc over lambda kBt minus 1 bracket close. We need to find the wavelength at which the flux is maximum. Therefore, we will take the derivative of flux with respect to wavelength. The derivative of flux with respect to wavelength is equal to 0 at the peak. The derivative of flux with respect to lambda is equal to 2 pi a c square derivative of 1 over lambda 5 bracket exponential hc over lambda kBt minus 1 bracket close with respect to lambda. We will do derivation by parts. Since derivative of flux with respect to lambda at the peak is equal to 0, we get the expression AC multiplied by exponential AC over lambda kBt divided by lambda kBt bracket exponential AC over lambda kBt minus 1 bracket close is equal to 5. If we set y is equal to AC over lambda kBt, we get the expression y multiplied by exponential y divided by bracket exponential y minus 1 bracket close is equal to 5. From this expression, we find y is equal to 4.965, which means Hc over lambda kBt is equal to 4.965. Lambda max is equal to Hc divided by 4.965 kBt. H is the Planck's constant and has a value of 6.63 into 10 raised to power minus 34. C is the speed of light and has a value of 3 into 10 raised to power 8. Kb is the Boltzmann constant and has a value of 1.38 into 10 raised to power minus 23. Therefore, lambda max is equal to 0.0029 divided by T. Lambda max is inversely proportional to temperature, which means as the temperature increases, maximum intensity occurs at a lower wavelength. B is Wien's displacement constant and has a value of 2.9 into 10 raised to power minus 3 meter Kelvin. The theoretical calculation completely agrees with the experimental observation. The value of Planck constant H is equal to 6.62 into 10 raised to power minus 34 joules per hertz. Planck length LP is equal to under root h bar g divided by c cube. H bar is reduced Planck constant and is equal to h over 2 pi. That has a value of 1.054 into 10 raised to power minus 34 joules second. G is Newton's gravitational constant and has a value of 6.67 into 10 raised to power minus 11 Newton meter square divided by kg square. C, the speed of light is equal to 3 into 10 raised to power 8 meter per second. Planck length is equal to 1.61 into 10 raised to power minus 35 meter. So small that classical physics break down. Heisenberg uncertainty principle takes over. Planck mass MP is equal to under root h bar c divided by g. That is equal to 2.17 into 10 raised to power minus 8 kg. That is about the mass of a speck of a dust. Planck time Tp is equal to under root h bar g divided by c to the power of 5. It is equal to 5.39 into 10 raised to power minus 44 second. It is so small that the uncertainty principle takes over. Planck temperature Tp is equal to under root h bar c to the power of 5 divided by g kb square. H bar is reduced Planck constant, c is the speed of light, g is Newton's gravitational constant, kb is the Boltzmann constant. Planck temperature has a value of 1.41 into 10 raised to power 32 Kelvin. Such a high temperature that black holes can form. Niels Bohr, Max Planck and Einstein are founding fathers of quantum mechanics. They were also awarded Nobel Prize for their work on quanta. A quantum plural quanti is the smallest discrete unit of phenomena. Quanta of light is photon, quanta of sound is phonon. The magnon is spin wave quantum. Spin waves propagate in magnetic material. Graviton is the hypothetical quantum of gravity. May Allah bless us all. Thank you for watching. Allah Hafiz.